Okay, good evening. Welcome to Geometry Project number 13. Unlike last two sections, this section has quite a lot of substance. In fact, I may have to split this section into two lectures today and tomorrow because I don't know that I can fit it all within 15 minutes. In any case, we're looking at section 2.4 of Geometry Revisited, more on altitudes and the orthocenter of a triangle. So, we start off with the following picture: triangle ABC, circumscribed circle. The altitude from A down to the side BC, which intersects at D. The book calls that HA. I've drawn the circumcenter at O, along with a line down to L. This, you'll recall, is a perpendicular bisector of the side BC. L is where it intersects the circle. And I've also drawn the line A to A0, which is a diameter of the circumscribed circle. So, what can we say on inspection of this triangle? The first interesting result they derive is, since angle ABC cuts off that arc of the circle, which is the same as angle A0C here, that means that the angle at B and the angle at A0C are the same. And because then this implies that triangle ABD is similar to triangle where's the hypotenuse? AC naught. Did I say that right? No, sorry, here's the hypotenuse. A naught C. Okay, here's the hypotenuse of this right triangle. A naught is the hypotenuse. By similar sides, HA over C equals B over AA naught. But this is just equal to B over twice the radius of the circumscribed circle. And so we get a simple formula for the altitude, that the altitude from vertex A equals CB over 2 times the radius of the circumscribed circle. So that's a nice little formula. You can derive this formula for the length of an altitude very easily. You'll also remember from section 1.1 of Geometry Revisited, we derived a formula for the area equals ABC over 4R, and you can infer this from recognizing that this is just 1/2 base times height. Base times height. The height is A. The length of the height is HA. The base is side A. And you can derive this formula as well. So we've actually seen a version of this before. The other interesting thing they look at in this beginning section here is they ask the question, what is this angle here? So what is the angle that the altitude makes with the diameter? So what can we say about that? Well, you recall these two angles are equal. And that means these two angles are equal. I'll just fill them in up here. This angle is equal to this angle, and they're both 90 minus B. So the angle that we're looking for, DAA naught, angle DAA naught, this equals angle A minus twice 90 minus B. Because I'm taking, this is 90 minus B and this is 90 minus B, which equals A minus 180 plus 2B. Let me just write A plus 2B minus 180. Now you'll recall from your beginning geometry class that 180 is equal to the sum of the angles of the triangle. So this is equal to A plus 2B minus A plus B plus C. And so this just equals B minus C. So we get a really nice formula, and a very simple formula, for the angle that the altitude intersects the diameter of the circumscribed circle intersecting the same vertex. Now, I should say this formula comes about when B is greater than C. If C was greater than B, the exact same arguments would have said C minus B. So what we really need to do is just put an absolute value on that, because you don't know ahead of time which angle is bigger. Okay, so these are the first two kind of fun facts, and I think I am going to split today's section into two separate lectures. So we're just going to look at the next fun fact and call it a day. All right, so let me draw the next picture. Okay, so here is the second section, section 2.4. We're going to look at some facts about the altitudes and how they interact with the circumscribed circle of the triangle ABC. So I guess I better put away my red marker and grab a black marker. The first thing the book points out is we've got a right triangle here, ABD, and we have a right triangle here, FCB. Okay, so we have ADB and CFB. They both are right triangles that have the same angle B in them, and that's going to tell us that this angle equals this angle. Well, that's pretty nice to know. The other thing that you can see is angle A cuts out this arc of the circle here from B to D. So angle A goes to B and into D prime. Sorry, B to D prime. Also note this angle here, BCD prime, cuts out exactly the same arc. And that means we can add to our list of angles that are equal here this angle. So BCD prime equals BCF equals BAD. So we found three equal angles in this circle. Oh, jeez. And I'm sorry, it's clear from the picture, I hope, but what D prime, E prime, and F prime are when you take the altitudes and extend them, and it's where they intersect the circumscribed circle. That's what D prime is. But now we have a very interesting observation that I guess I'll draw in purple. This triangle, CDD prime, is a right triangle with a right angle at D and this angle here, and at C. And the right triangle HDC is another right triangle. Now this has the same angle, so these are similar right triangles, but they also share a common side. And that means these two triangles are actually congruent, which gives us our first interesting little fact that when you draw this figure, draw a triangle, draw its altitudes, extend those altitudes out to the circumscribed circle, we know that HD equals DD prime. In other words, the distance from where the altitudes intersect, the orthocenter, to the triangle, is the same as from that point where the altitude hits the triangle, the foot of the altitude, to the circumscribed circle. Similarly, HE, this is going to hold true for all the altitudes, HE equals HE prime, and HF equals HF prime. So there's a fascinating fact that I had never seen before about altitudes and the circumscribed triangle. And one last fact that's a little harder to draw, but I'll do my best in green. We're going to look at the circle whose diameter is AB. And you'll notice that there's a right angle at D, which means that's inscribed. BDA has the diameter AB, and BEA has a diameter AB. And that means if when I draw this circle, it's going to hit at E, it's going to hit at D, and it's going to hit at B, and then it'll be over here somewhere too. And the diameter is AB. Well, this is an interesting. From this diagram, you see that AHD is a chord and a chord of the circle, and BHE is a chord of this circle. But we know from a theorem we proved, I think in section 2.1, that means that BH times HE equals AH times HD. And by the way, it's going to also equal CH by the same argument times HF. In other words, the way the altitudes intersect with each other, they intersect in such a way that AH times HD equals BH times HE equals CH times HF, which is another fact about the altitudes I had never known before reading this section. Fun fact about the altitudes and also about the distance to the circumscribed circle. So, two easy theorems here, and tomorrow we're going to prove one very hard theorem that comes at the back of this book that I would not have had time to do today. So, thanks for watching. We'll finish up this section tomorrow.